Okay, so question 6, they've given us the equation. They've told us y equals f at x. Okay, so essentially what they're telling you is just your y-axis here. Y equals f at x. Okay, essentially this function. Okay, we need to actually find the equation of this function in order to create a reciprocal function. So this is linear. Do you remember finding linear equations at all?
Kind of.
Kinda? Okay. Formula for linear equations, y equals mx plus b, right? We can create it. From looking at this, I can pretty much find the slope. We could always find 2 points, but a quick way of doing this would just kind of be when we go over one, we go down one. It is a constant rate of change. So the slope is over one downward. So for rise over run, we go to the right one and we go down one. So we go down one to the right one, essentially. That's the idea. Down one, right one, down one, right one. So our slope is -1. Does that make sense? Okay. Our y-intercept is at -1. So the equation, y equals -x minus 1. I did that quickly. You okay with that?
Yeah.
Okay. Since that's our function, so with that being said, we found our function. Okay. So essentially what they want us to do, just like our formula we've written over here, this function, we can replace y with f at x since y is equal to f at x. Essentially the function is f at x is equal to -x minus y. So to find the reciprocal function, which would be 1 over f at x, is just 1 over -x minus y. That's all we have to do for that question. Is it? Sketch. Now sketch the graph. Oh, okay. So they want us to take it a little farther. Alright, so find vertical asymptote, we have to find out what x is not equal to. So the idea to this is, because this is above 1, the only number essentially 1 can't be divided by would be 0. Okay? So essentially, y can never equal that. Or f at x can't equal that, right? 1 over 0. So what we're doing is we'll constantly set the bottom, or the original equation, equal to 0 to find a vertical asymptote. So we take our -x minus 1, set equal to 0. We move 1 over, we get 1, and we divide by -1. Which makes sense, because when we go to plug it into that equation, even though it looks a little funny, it would be -1 minus 1, which would cause 1 minus 1, which would be our 0. Okay?
Yeah.
So essentially our vertical asymptote is at -1. We'll draw it here. We can never touch that. Because this is a positive, we're going to be going from quadrant 3 to quadrant 1. Yeah. Yes. Our x-axis will be our horizontal asymptote with our reciprocals. So this will be our horizontal axis. And we essentially have something like this. Oh, I think I've drawn this backwards. Oh, our x is negative, sorry. So we can factor this equation, and essentially f at x, this makes it a negative equation. It's like saying we factored -1 out, and we'd have 1 over x plus 1, right? So essentially we're multiplying whatever this function is by -1, so it's a negative reciprocal. So normally we go from quadrant 3 to quadrant 1 when we're positive, but since this is a negative reciprocal, we're going to go from quadrant 2 to quadrant. Try to think of the function just like we had before. F at x is equal to a of the function k. Is it d? I think the letter you guys use, plus c, like that. Yeah. So our function, our f stands for our reciprocal in this one. So in other words, essentially our function is going to be a 1 over kx minus d. That's how this is going to affect it, plus c. Okay? So any horizontal shifts, stuff like that, are affected underneath, 1 divided by them, and a will be our number multiplied on the outside. Remember, it gives us a reflection on the x-axis, which is essentially what we found here. We found an a value of -1, so we reflected it on the x-axis. And if there were any values of c, we'd be moving it up and down.
So when you
Okay, this is a calculus type idea. It's called a limit. So what we're going to be doing is f at x, okay, and the limit. So essentially we're finding a horizontal asymptote as x approaches the number infinity. Okay, so essentially think of it as the idea is x is going to become infinity. So we take our function, and what we're actually going to be doing is we're going to divide every term by the lowest variable exponent. So in other words, what I'm saying is our lowest variable exponent is x to the power of 1. As you go into tomorrow's lesson and the lesson after that, you'll start to get where x is 3, x is 2. If there's ever an x to the power of 1 in it, you have to divide by that. That's the function we divide by. So because this is x to the power of 1, I'm going to divide all of these. So 1 divided by -x divided by, subtract 1. We're dividing everything by x. Okay? Is this okay so far? This is one part of the process. As we do that, we have to keep in mind that we're saying as x approaches infinity. So essentially, we think of the idea as x being an infinitely large number, extremely large. So large that if you divide a constant by it, it essentially becomes 0. Okay, that's how large this number is. Think of it like, I guess the best way to describe it would be like, I'm not sure how far this calculated, divided by this. Calculator only goes so well. Oh wow, it goes really far. Calculator won't even do it. It's such a small, minute number. Okay, so what you can do is replace the x's with the infinity sign if you want to make sense of this. So in this one we have negative infinity divided by infinity, okay, minus 1 divided by infinity. Anytime we divide a number by infinity, it's going to be 0. Okay, essentially that's what our calculator gave us. It gave us 0 as our number. So our number on top will become 0. Now infinity divided by infinity is the same idea as 1 divided by 1 or 2 divided by 2. What does it equal?
1.
Same with infinity. It's an infinitely large number. So we have 1, subtract, again, 0. Okay? So because we did that now, we have 0 over 1, which is equal to what? 0. This is our horizontal asymptote for this function. So when we went back, remember I just went about telling you that the horizontal asymptote was right across the x-axis? So our horizontal asymptote, sorry, I should have find the letter in there, f at x or y, or f at x is equal to 0. So the y value of the horizontal asymptote is 0. So that's how we know what not to touch horizontally, and vertically we are setting the bottom of the equation equal to 0.
Okay.
Just as a side note, what will help you with slope, say we have a linear equation on the bottom, which we had. Remember that our equation went through, what did it go through? -1 and -1. So eventually it was going like that, and it was going, that's okay, like that. So if you notice, it went almost pretty much through the 2 turning points here.
Okay.
Essentially, this is when we really change directions. It'll help you remember slope. So if you ever have a linear equation, and I drew something like this for the reciprocal, we know that's not right because our linear equation isn't actually going through our 2 reciprocal functions. So that means we've graphed it incorrectly. Okay, so let's look at this function. We know it's the original function, f at x, is just the absolute value of x, right? With that function, it's normally, do the dotted one, it's a 45-degree angle when it's on. Now what we didn't notice before was that the slopes of these absolute value essentially have changed. Instead of going over 1 up 1, like they normally do, okay? So absolute value of 1 is 1. Absolute value of 2 is 2. And absolute value of -1 is 1. That's the idea.
Right.
Here we're going, we've shifted down 2. So you did notice that. It's related to our parent function, f at x equals a absolute value of k x minus t absolute value plus c. Now we knew C moved us up and down. And you notice that C in this one's going to be -2 because our, I guess you could say the vertex of this absolute value, or our original point or origin, is at -2. So our C value is going to be -2. But the problem is we've been horizontally, two ways of putting it. We've been vertically compressed or we've been horizontally stretched. Either way, because of the slope of this now. Okay. So normally our A function is 1. So let's say it's a vertical compression. Normally A is 1. In this case, when we go over 1, we're going, over 1, 2, 3, up 2. So it's almost like a slope. We've gone, I want to say, compressed by a factor of 2 over 3 is our new A. It's essentially a way of looking at it, as our slope has changed by going over 3, up 1. Or up 2. So this is our run and our rise of it. So what we should be doing is applying this into the function. Let's assume this is our A value. I should double check that. So assuming our A value and our C value are right, we're going to make this a reciprocal function now. We'll do it in red. So our f at x of this should be 1 over that entire function, which is 2 over 3 absolute value minus 2, right? Now we're looking for when the bottom of this equation can't be 0, okay? So in other words, we set 0 equal to the bottom or the denominator of it. So we have 2 over 3 absolute value of x minus 2. We're going to bring 2 to the other side, so that becomes positive 2. We have 2 over 3x, and technically we need to multiply this by 3 and then divide by 2. In other words, we need to flip the fraction when we bring it to the other side. Does that the idea make sense? Okay, good. So when we flip the fraction, we'll end up with 2 times 3 over 2 equals absolute value of x. We multiply through, we're going to get 6 divided by 2 is the absolute value of x. So we got 3. Now, technically is the absolute value of x. Because this is absolute, our answer then becomes positive or -3, because we know either one we put in is going to equal just positive 3 in the absolute terms. Does that make sense?
Yeah.
So our vertical asymptotes then for this equation, let's do it in green, are going to be positive and -3. Say I ran the limit rule. Essentially what we're going to find is our horizontal asymptote for the reciprocal function is going to be the x-axis or 0. Okay. Now we have a, what was our actual equation in the end? Here it was, right? This was our equation. We got it to be this. Now it is a positive function.
I just don't get why they're...
So one way to test what our function is going to look like is give values of y. So I know we have a lot going on in this graph, but for instance, we know that it's going to cross positive 1 for y at some point. So let's find out what those points will be, because essentially it'll either tell us that we're in between them or we're outside them. If we're outside them, then we're going to have something like this and like this. We'll have 2 points, and then that means we'll have this in between. Okay, this is a sketch of the graph. It's not an actual graph of it. If it tells us we're in between, though, at y positive 1, then we're going to have something like this. The loop will be in between, and the other 2 points will be outside like this. So we're going to solve for our values when y is 1. So we're going to plug in a value or f at x or y is 1. So let me just put a little separator here. Okay. So we need to find when f at x, or when f is at, not when f is at 1, sorry, when f at x is 1. So our reciprocal function here, 2 over 3 absolute value minus 2. So when y is 1, that's what we're looking for now. Y is equal to 2 over 3 absolute value of x minus 2. Now, what I want to do is I want to take this entire part and move it to this side. Okay? Do you know how I do that?
Do you flip the fraction?
kind of think of this is a big division sign. So in order to move this, because it's divided by, I'm going to need to multiply both sides by that. Now when I multiply both sides by that, we'll do it in red, okay? 2 over 3 absolute value of x minus 2 times the original 1 over there, which we know is just going to give us that. On this side, when we multiply it by that, we'll have 2 over 3 absolute value of x minus 2 times the 1 on top, and then on the bottom we have the exact same thing written out. So what ends up happening over here? Yeah, that's right. These two cancel out, so what am I left with on the right side?
1.
Just 1. Okay. So we have, and then on the left side, that 1 is essentially that function, right? 1 times that will just leave us that. So we get 2 over 3 absolute value of x minus 2 is equal to positive 1. We move the 2 to the other side, it becomes positive, so we have 2 over 3 absolute value of x is equal to 3. That makes sense? Okay, and now we have to move this fraction over. Same idea, it flips again. So we get the absolute value of 3 times 3 over 2. And we get, our x values are going to be 9 over 2 or 4.5. Okay? Our x values are going to be 4.5. So what I'm going to do is I'm going to relate that to the graph. So according to this, our x values are positive and negative 4.5 and 1. So we have two coordinates. One of the coordinates is negative 4.5. And remember, we plugged in y at 1. So that's our y coordinate. And our x coordinate is 4.5 and y is 1. Okay? We knew we were going to get 2 because it was absolute value. So now we go and take a look at that on the graph. When x is negative 4.5, that's here. Great, we're touching right on it. And when it's positive 4.5, we're here. So now I know I'm above my horizontal asymptote. So I know when I go to graph this function, we'll do it in red, it's going to have to go like this. Okay?
Is that going to happen whenever there's an absolute value of x?
Yeah.
And
now,
if it was negative, they'd be on the bottom?
I would use this test here. I'll look over the rule again, but use this test just to double check. Now, as we approach this asymptote, we'll never touch it, and then eventually we'll come up from it. It'll do something like this. We haven't actually solved for what's in there right now, so this is just a rough sketch. And then finally, it comes down from that asymptote and across. Okay? So because we knew when y was 1, we were above the horizontal asymptotes, we know that the sketch of this graph is going to be above and above in quadrants 1 and 3, and then in between we're going to be below. Is that?
Yeah.
Is that?
Circle and so.
Yeah, I wouldn't touch it since grade 10. Circle functions are x squared plus y squared is equal to the radius of the circle squared. Now, because our center of the circle is at the origin, we don't have to do any shifts or anything with this function, because technically the parent function, I think, is x minus h squared plus y plus k, I think, squared equals r squared. So because the center of the circle is at the origin, we can work with our first parent function here. What's the radius of this circle? 6. So we would plug 6 in, and we have x squared plus y squared is equal to 6 squared, which is x squared plus y squared is equal to 36 squared. Okay? So we need to set this equal to y. So we're going to move x squared to the other side. So we're left with y squared is equal to 36 minus x squared. And then in order to get this as just y, we need to square root both sides. So we're going to get y is equal to 6 minus x. We're able to find the square roots of both of those, right? Oh, what's funny is that gives us a linear equation.